Okay, I'm going to questions today because I just want to get to a point where you can do some problems over the weekend. Um, so we're going back to rotating coordinate systems, particle kinematics in rotating coordinate systems. And there are really kind of three results. And okay, there are three equations that sort of matter. The first one is how you derive the second two, but it's the second two that we're really going to use. So big result. Trademark says that for any vector, and it's hard to imagine this in any way except kinematics vectors, but I mean, this could be a force vector or any vector you can imagine, anything that's a vector. If you're taking a time derivative in a rotating coordinate system, it's gonna be the time derivatives of the components, and that by itself is what we usually think of as that's usually in a non-rotating coordinate system, that's the end of the time derivative of a vector. But then we also have to add on this correction term. And we can also write this in this equivalent way. Oh, this needs to be a time derivative, sorry. That's sort of the key to this whole thing. So this expression is how you take the time derivative of a vector u. Equivalently, you can think of this as the time derivative that's observed. That's what would be measured to somebody living in that rotating coordinate system, plus this correction term. But right now, I'm not going to put a box around this because really these aren't the ones we're going to use. What we're going to use is that from these you can derive the velocity and acceleration expressions. So the velocity in a rotating coordinate system is equal to the time derivatives of the components of the position plus omega cross position vector. And you can also think of this way. The velocity vector is equal to the observed velocity vector plus the stuff that someone living in a rotating coordinate system would not see, and that's this. And then the acceleration vector is the second time derivatives of the components of the position plus the time derivative of the angular velocity of the coordinate system crossed with the position vector. That one looks like a term in the watermelon equation. Plus 2 times capital omega crossed with the first time derivatives of the components of the position vector. Plus the next term that looks like a term in the watermelon equation, omega cross with the quantity omega cross p. Or equivalently, the acceleration is equal to the observed acceleration plus capital omega dot cross p plus 2 times omega crossed with the observed velocity plus omega cross quantity omega cross p. And which one of these forms you use is just determined by what you're given in the problem. If you're given a way to calculate these time derivatives, if you're given the position as a function of time, then this is the one you want. But if instead you're given stuff, we'll see a lot of cases where we set up our coordinate system in a way because it's easy to tell what you would observe in those cases. So each of those is useful in a different, it's not like, oh, I choose this one because I like making dots or whatever. Each one is useful in different applications. Okay, so these are the two things we're going to use, the expression for the velocity and the expression for the acceleration. And the first example I'm going to do is polar coordinates, but before I go into that, I want to just introduce the example I'm going to give after that, because I think it brings up something important about what you have to consider with non-inertial coordinate systems. So I'll come back to this example. But for now, this is just this is like an illustration of inertial, inertial / non-inertial coordinate system things you have to watch out for. All right, so non-inertial coordinate systems, those are the ones that give us problems. If you have an inertial coordinate system, then no problem. Calculate the acceleration, and from that acceleration, you can do kinetics. But if you have a non-inertial coordinate system, then you have to, it won't work with Newton's laws. Okay, so how can a coordinate system be non-inertial? First, the origin can be accelerating. And besides that, you could have, okay, well, the origin can be accelerating. The coordinate system can be rotating. That's what we're doing now. That means that over time, the axes are changing orientation. And these aren't mutually exclusive, so you have to also consider the possibility that you have both of these two things going on. Okay. This one is easier to deal with. If the origin's accelerating, you're just going to use the relative motion equations. That's all you need to do to express that result in an inertial coordinate system. The rotating coordinate system one is the harder one. And that's the current topic. Okay, so this example that I want to draw to illustrate this is that astronaut and that training device thing. I've called it that training device thing like a million times in my life. I should just look up what it's actually called. I'm afraid I'll look it up and find out that it's only a movie thing and they don't even actually do this. Um, okay, so this thing is traveling in a circular path. And let's think of three coordinate systems. The first one is like this, and it's fixed. So and each of these coordinate systems you can think of as a video camera. Okay, that's what we're talking about. A video camera that you're using to take measurements. And so what this video camera sees is every second or whatever, this guy goes by and then is gone again until he comes back. Okay. And then there's a second one that looks just the same. It's in the same spot. But this one's rotating with the arm. So this video camera just sees a man that looks really unhappy for no reason the whole time. You know, it's just looking at this unhappy guy like, what's his problem? You know what I mean? And then the third one is fixed on the arm, and it's halfway out on the arm for the person. Um, and so this one also just, and it's just a video of this person just sitting there. Okay? And let's think about what we have in all three of these cases. That fixed coordinate system, the origin isn't moving, right? The coordinate system isn't rotating. So that's an inertial coordinate system. Okay? A video camera like that, whatever measurements you take of the acceleration from the video camera is good. You can use that for Newton's laws. Okay. The second, the dark green one, is rotating with the arm. Is the origin accelerating? No, the origin's staying in one place. All that's happening is the coordinate system's rotating. And so in that coordinate system, you would use the video camera to measure what you see as the acceleration. In this case, it would be 0 because you're just looking at the person sitting there. And then you apply the correction that comes from the rotating coordinate system, the stuff that we're doing right now. Okay. The blue one is like the deluxe model. You know what I mean? Because it's moving around in a big circle. That means it has at least centripetal acceleration if the velocity is constant, if the speed is constant. Sorry. Velocity is definitely not constant because it's in circular motion. And so for this, and besides that, so the origin is accelerating because it's moving in a circle. But besides that, the axes are changing orientation as the arm changes orientation. Okay. And so for this one, we need to use relative motion to correct for the fact that the origin is accelerating. And then we have to use the rotating coordinate system equations to correct for the fact that the axes are changing orientation. Okay. So I'll come back to that example, and I'm going to do all three of those calculations, and you'll see that when we do those corrections, it all comes out the same. Okay, so oops. This one is I guess based on the 1 and 2 above. The dark green is 2 only. The fixed coordinate system is inertial. And the blue one is 1 and 2. The origin is accelerating and the coordinate system is rotating. How would you get one that, like in this example, how would you get one that had an accelerating origin and not a rotating coordinate system? If you picture this thing being so just the x-axis is always pointing that way. So instead of rotating around like this with the arm, it's just going around in a circle like this. Okay. Then you would only need to worry about the origin accelerating, and you wouldn't have to worry about the rotating coordinate system. Okay, so I'll come back to that. The first example I want to do is polar coordinates. So polar coordinates, you think of like this. You have an object moving around. So here's the object. And you measure its location as a distance r from the origin and an angle theta counterclockwise from your sort of implied x-axis. Okay, so if this is the x-axis and this is the y-axis, you know that x is equal to r times cosine of theta, y is equal to r sine theta, r is equal to the Pythagorean theorem, so x squared plus y squared, so square root. And then theta is the inverse tangent of y over x. Those give relationships between the x, y coordinates and that fixed coordinate system and the polar coordinates. Okay, and this is sort of an unusual thing. Like when you are using an x, y coordinate system, your coordinates are the vector components of the position, right? The coordinates of the object are the components of the position vector. But that's not true anymore. The polar coordinates are r and theta. But those aren't vector components. There's no coordinate system that you can set up, no orthogonal, no coordinate system like we're used to, where r theta is a pair of vector components. Those aren't position vector components. Okay, so if we're going to do calculations dynamics calculations involving polar coordinates, we have to set up a coordinate system and come up with a position vector, not just coordinates like this. Okay. And so the position vector, the coordinate system origin that we're going to choose has one axis this way. That axis is going to be called the ER axis. And then the other axis is this way, perpendicular. And I'll call that the E theta axis. The what? Uh, yes, right. Um, and yes, you can use basically like these relationships are sort of like the rotation matrix to go back and forth. Okay, so if we want to represent a position vector in polar coordinates, we don't represent it as r theta. We represent it as some distance along ER plus some distance along E theta. Can you think of what the position vector would be in that coordinate system? I'll give you some time to just sort of get your bearings on this. I mean, like, if think about it this way, if this was the XY coordinate system, what would be the coordinates of that object? Yes, it would just be r in the x direction and 0 in the y direction. And so the position vector is r er plus 0 e theta. To get it into the form that we're used to dealing with, I'm going to write this as I guess I'll also say that we have a 0 component in the k direction. That's the same z direction, k direction as in the xy coordinate system. And so I'll write this as the vector r0, 0, where the r represents, the top one represents the er component. The middle one represents the e theta component, and the bottom one represents the k component. Yep, exactly. That's right. Yeah. Although I think the math works out if you wanted to point, yeah, always positive. Yes, for the position. And so at first you're like, what's the point of even having an E sub theta defining these other things if the position vector? But we're going to see what the point is when we calculate the velocity and the acceleration. Okay, so notice that what we have, I mean, our coordinate system is just, as that object moves around, ER just keeps pointing straight at it. And so the position vector is always just r0, 0. But also notice that as that thing moves around and this thing is rotating, the origin stays in place. So it's not an accelerating origin, but it is a rotating coordinate system. The orientations of those axes are changing. Okay, so the origin isn't accelerating, but the coordinate system is rotating. So we're going to use what we know about that to calculate the velocity vector and the acceleration vector. Okay, well, the velocity vector is, we'll think of this as the components of the position vector. And I'm used to writing it px, py, pz, but in this case, we have a different, these have different names. So I'm going to call this pr, p theta, p z, whatever, dotted. Plus capital omega crossed with the position vector. And now we're going to just start to fill in these values. What do we know about omega? The angular velocity. What? It's non-zero. And we can actually give a relationship between that vector and this theta. So remember that when you're talking about motion in a plane, the angular velocity is just the time derivative of the angle. And so the capital omega vector is just going to be 0, 0, and then theta dot in the z direction. Okay, are you with me on that? Okay, so take the time derivative of the x component, the r component of the position. You get r dot. These other two are always 0, so the time derivative of a 0 function is 0. Then capital omega is 0, 0, theta dot. And we're crossing that with the position vector, which is r, 0, 0. And so we get r dot and then in the theta direction, r theta dot, and then 0 in the z direction. So, or you can also write it as r dot in the er direction plus r theta dot in the e theta direction. Now you see why, to calculate the velocity, that e theta axis comes into it, okay? Because of the correction that we had to make due to rotating coordinate system. If it wasn't a rotating coordinate system, this would just be the end of it for calculating the velocity in a polar coordinate system. But when you apply the correction, you find out that there is a e theta term. And I'm curious, did any of you remember seeing anything like this in, I know you haven't seen like the derivation and stuff using this approach, but yeah, I was hoping that at least some of you had seen expressions for the velocity and acceleration in polar coordinates. And you're sort of like, where does all this mess come from? But it's pretty easy to derive if you just think of this as a rotating coordinate system and you're just applying those rules. Any questions about that before I go to acceleration? Okay, so acceleration in a rotating coordinate system is the second time derivatives of the components of the position vector plus omega dot crossed with the position vector plus 2 times omega crossed with the first time derivatives of the components of the position plus omega cross quantity omega cross p. So plug in what we know. What are the second? So first, let's calculate the second time derivatives of the components of the position vector. What's the x component, second time derivative? Yep, r double dot. Theta, second time derivative, 0. And then z, 0 also. Yep. And now we're taking the time derivative of the expression for omega. Remember that I mentioned last time that the time derivative of the omega vector is just equal to the time derivatives of the components. And so this is just going to be 0, 0, theta double dot. And we're going to cross that with the position vector, which is r, 0, 0. And then we have 2 times the vector 0, 0, theta dot crossed with r dot 0, 0. And then we have 0, 0, theta dot crossed with the quantity 0, 0, theta dot crossed with r, 0, 0. First, the second term just gives us 0, r, theta double dot, 0. The third term gives us r dot theta dot times 2 in the the theta direction. So that's 0, r dot theta dot times 2, and then 0. And then this one gives us 0, r theta dot 0. And so both of these together give us negative r theta dot squared 0, 0, I think. This one we didn't do anything to. Our final expression for the acceleration is the first component is r double dot minus r theta dot squared. The second component is, the way people usually write it, is 2 r dot theta dot plus r theta double dot. And the third component is 0. Okay, so um, to use these, let's say we have an object with a mass of 0.01 kilograms, and it's moving according to r is equal to 5t, let's make that squared, and theta is equal to t. What's the net force on this object? To go from particle kinematics to particle kinetics, we know we need to get the acceleration. So we can use the acceleration formula that we just calculated for polar coordinates to come up with the acceleration. And then the net force is just the mass times the acceleration. So is everyone with me on what we're doing here? Anybody have any questions? Yeah. To find V? Well, I did this the same way that I did it for the general expression for the acceleration. Well, right. You don't have to do that because we're not asking for velocity. Um, if if this question asked for velocity, you would have to do that. Since it's only asking for net force and net force only cares about acceleration, then we're just going to jump right to acceleration. That's why acceleration is what you want more often than, because that's how you calculate forces. Um, okay, so we know that the acceleration is equal to r double dot minus r theta dot squared, and then 2 r dot theta dot plus r theta double dot. I'll just leave the z component off this time. By the way, if you don't leave the z component off, it's just cylindrical coordinates and everything else is the same since that axis doesn't change. So plug these values in. The acceleration is equal to the second time derivative of 5t squared. So that's 10t, so 10 minus 5t squared times 1 squared. And the second expression, the second component, we have 2 times 10t times 1 plus 5t squared times the second time derivative of t is just 0. So our acceleration as a function of time is 10 minus 5t squared for the first component. And for the second component, it's 20t. And so Newton's second law says that the net force on this object as a function of time is 0.01, that's the mass, times the acceleration, and that's 0.1 minus 0.05 e squared, and then 0.2 t. Any questions about that? And so this is a pretty, common thing that you would have if you're using a polar coordinate system. That you just be given r and theta, the two coordinates, as functions of time. And now we have expressions. You can use those to come up with a position vector, a velocity vector, acceleration vector as a function of time. At least the first one problem on the new problem set uses this kind of stuff. So you can sort of get used to it. Okay, last chance. Any questions? Last call. Okay, have a good weekend.